Okay, welcome back to what will be the last topic in the course, unless I totally have my weeks wrong, in which case I apologize. So today we're talking about correlations. So now we know, now we have a new graphic here. However, don't be frightened because we're covering this all today, right? So this is still the last one of these that you'll see. So at this case, like I just made like an entirely new graphic because we're kind of looking at some different things here. So overall, now we're looking at tests for relationships between variables, and you can see different decision points and different correlations that correspond with those. First, let's go high level. What is a correlation? And I guess I'll start by saying that this is a word that I think has kind of entered the lexicon. I've heard this in context completely unrelated to statistics. So you might have heard people say things are correlated. You might have even come across correlations in other classes. Um, in this context, this is a statistical procedure, right? And basically what we're doing here is describing the strength and direction of a relationship between two factors, or in other words, we are describing the relationship between two factors in terms of a line, right? A line that fits the data and essentially portrays the relationship in terms of its strength and direction, right? So we'll get to that in more depth. So here we're talking about variables. Basically, I'll skip some of this. You can come back and look at it if you want. Just for the sake of time, we'll skip some of the minor details. But in this case, there are different ways we could look at this. Broadly speaking, like I said, we're describing a linear relationship. Linear just means a straight line. So a linear relationship between two factors. And typically we'll illustrate these through a scatter plot. So you can see one right here. And so any scatter plot is illustrating the relationship between two variables, the x and the y. So in this case, general well-being and depression. And so each data point here, each of these little dots or circles, represents one participant's score for x and for y. So for this person right here, it looks like their general well-being was probably like 108-ish, 109-ish, and their depression was like, I don't know, 75-ish, something like that. Right, and so each of these correspond to one participant, and then collectively, we're basically doing a statistical analysis on all of these data points to identify what is the pattern of the relationship in the form of a straight line, right? Kind of reducing all this noise down to one single number that indicates that. And so that number is the correlation coefficient. You can see here lowercase r. And so this, like we've said just a couple slides ago, this will indicate the strength and direction of the relationship, and the term correlation refers specifically to that relationship, right? So correlation is the relationship, correlation coefficient is the r, the actual value. And this can range from -1 to +1. So it can be minus 0.968, or it could be positive 0.024, right? It could be anything in between. And so importantly here, the absolute value, or just the number, that indicates only the strength, right? So closer to 1, whether it's positive or whether it's negative, means it's stronger. A correlation of 0.2 is stronger than a correlation of 0.1. And a correlation of minus 0.8 is stronger than a correlation of minus 0.6, right? Because they're closer to plus or minus 1. And then the sign, that minus or positive, refers to the direction of the correlation, right? That's all that the sign is telling us, right? Which direction it goes. And so to explain that in more depth, positive means they increase or decrease together. So this would be 0, or an r between 0 and +1. And so, in other words, like if we have variable A and variable B and a positive relationship, right, that means as one increases, the other increases. Therefore, we'll see this as a line that is slanted up to the right? It's like, if you remember from like, what class would that be? Geometry, I think. When you had to plot X, Y charts on lines, you had to plot X, Y lines. You had to plot lines on X, Y charts. There we go. You can tell it's been a while since I've taken that course. But if you remember the slope of lines is positive or negative, that's essentially what the positive and negative means here. So this would be a line with a positive slope, right? As one increases, as X increases, the Y is also increasing, right? So it's a line that trends up to the right. And that line here is what we call a regression line. This is, yeah, kind of within a family of statistics referred to as regression. So like when we do these in Jamovi, we'll actually have to click a button that says regression. So yeah, it's best fitting line. Basically, it's the best attempt to map out the relationship between these variables. A negative then means they increase or decrease inversely. So as one goes up, the other goes down, and vice versa. And so this will be in line with a negative slope, right, intuitively. So as one increases, as x increases, here y is actually going down, right, and vice versa. So just to kind of like think about this conceptually, I want you to think these two variables, will they be positively or negatively related? Test anxiety and test scores. Go and pause the video and think about it. And assuming you did that, here these would be negative, right? The more test anxiety one has, presumably the worse we're going to do, right? Because we're too busy stressing to actually perform well. What about this one? Hours spent studying and test scores. This one's probably positive, right? Assuming that you're using good study strategies and you're not just sleeping with your face on your book. It's a strategy I tried a lot in undergrad, but it never worked for me. Right, but here we would assume these are positively related because the more we study, generally the better we're going to do on the tests, to an extent. Okay, and so to kind of elaborate a bit more on this, like we said, the strength is indicated by the absolute value of R, so closer to 1, whether it's positive or whether it's negative. Yeah, no, we don't need to get into all that. And so to kind of depict this graphically here, so you can see when there's no correlation, or yeah, to explain the A and the B circles here. Some people, the scatter charts don't really click for, so sometimes Venn diagrams can help if you'd like another visual aid. So you can think of like the strength of the correlation is indicated by the overlap of the Venn diagram. So here we have a correlation of 0, so the circles are not overlapping at all, right? They're separate, right? And so in the scatter plot, you can see there's no clear line we could draw through this that explains the relationship, right? They're kind of scattered everywhere. And then as our correlation increases in strength, in this case positively, it overlaps more, and then at a correlation of 1, it's essentially overlapping entirely. So you can see at 0.5, it's a more consistent scatter plot. 0.9, it's even closer, and then at 1, it's essentially a straight line, right? Because they are essentially the same at that point. If we see a correlation of a correlation of 1 in any of our work, it probably means that we're measuring the same thing twice without meaning to, right? That's probably not good, actually. So usually we'll see correlations that are less than that. Yeah, and then going in the other direction, it's the same concept. It's just a matter of the slope of the line, right? The direction of the relationship. But you can see here, there's still increases in consistency. It's just sloping downward now instead of upward. And so there's all that on one slide if you'd like to come back and look at it. We have assumptions here. Once again, I don't want to spend a lot of time on this in the video because it's important, but it's not what I want to spend most of our time on. So homoscedasticity, broadly speaking, it's the assumption that there's equal variance. So if you'd like a visual aid here, right, this is a violation because the variance is unequal throughout the extent of the relationship as we could graph it. Linearity, we assume a straight line, right? In this case, this violates it because it's a curved line. Yeah, normality, yeah, we don't need to worry about that one. Causality, you can come back to this because I'm about to explain it in more depth. So, you might have heard the phrase correlation does not equal causation. I'd like to briefly discuss that now. So let's say, hypothetically, that a researcher is studying motivation and college performance and finds that the two are related, right? So in R.5, so generally it seems like as motivation increases, performance increases and vice versa. And so what are the underlying mechanisms that explain this relationship? Let's speculate, right? And first to give you a sense of where we're at, right? This is our correlation down here, 0.5. Well, for starters, maybe it's that motivation causes performance, right? If we're trying to think about causality here, maybe motivation, when we're motivated, it causes us to perform well, right? The more motivated we are, just the better we do, right? If you're motivated to go work out, usually you have a lot better workout than when you're not motivated. So maybe it's that. Well, that's intuitive enough, but maybe the opposite's kind of true. Maybe it's that the better we're doing, the more motivated we are to succeed, right? It's kind of like we're getting positive feedback, so it's reinforcing it. If you want to go back to um, operant conditioning and intro psych, right? So maybe it's something like that, right? You get good grades, you're more motivated to continue doing that. Okay, or maybe it's that they're kind of both influencing each other then, right? So like it's this feedback loop of doing well, being motivated to do well, and then doing better and yada yada. But maybe it actually has nothing to do with that. Maybe it's me. I am so damn good as an instructor that you're just motivated and you're performing well, right? So it's absolutely my responsibility, right? I can take all the credit. Or maybe it actually has nothing to do with me and I'm just letting myself get a big head. And really, it has something to do with you and its other characteristics, right? Maybe students who are conscientious, if you're just a good student, you will be motivated and perform well, right? Because you're disciplined, you schedule things, you manage your time wisely, so on and so forth. Maybe it actually has nothing to do with that, and maybe it just has to do with how well you slept the night before. Sleep's one of those things we often overlook, but actually plays a huge role in everything. So maybe it's that, right? Or hopefully you're getting my point that this could be a million things, right? And so when we say correlation does not equal causation, that's what we mean. We mean that we cannot infer causality or say that one thing causes another simply because they are correlated, because we do not know the nature of that relationship, right? We need experimentation, much more rigorous methods in order to identify that, right? It has less to do with the number that we get and more to do with the methods we use to get that number. And correlation is just an analysis, so correlation is not going to tell us that by itself, right? So yeah, for an example of correlation and causation, this is a really pixelated comic here, and so it's this little kid on an airplane and bouncing around, and he says, "I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy." Right? So that's a classic bias or fallacy, right? In judgment, thinking that it gets bumpy because they turn the seatbelt on. So this is misunderstanding correlation and causation. Okay, so hopefully that helped to explain that a bit. Outliers can also be problematic. Just like they can pull the mean, they can pull a correlation as well. So you can see some examples here if you want to come back to that. Restriction of range, basically meaning that we need to look at the full extent of the full range of the relationship, not just pieces, because we'll miss some of it. Anyway, yeah, so like I said, you can come back to that, but I want to spend more time on this. These are the correlation coefficients we'll go through. So first, let's start with Pearson. So in this case, we have two continuous variables, or two continuous factors. Right? So this is a Pearson, what we call a product moment correlation, or just Pearson correlation coefficient. So yeah, two factors linear relationship, interval or ratio, in other words, they're continuous. Here's our formula. The numerator is reflecting the covariance, or the extent to which the values on the x and y axis vary together. And the denominator is the extent to which they vary independently, right? So kind of like an ANOVA, which was a measure of between groups to within groups variance. This is uh, kind of similar, right? And saying it's how much they vary together versus how much they vary independently or separately, right? So an example, health psychologist measures the relationship between mood and eating. They measure mood using a 9-point rating scale. So higher ratings indicates better mood. A 9 is a better mood than an 8, so on and so forth. They measure eating as average calories in the previous week. Mine was way too high. It's been one of those weeks. Okay, so we got the results on the next slide. That's what we want to do a correlation. So you can see here, we have mood, we have eating, we have our graph. Well, I'd like you to think first off, is this going to be positive or negative based off what you see here? The answer should be that it's going to be negative, right, based off the slope of the line. So let's do this. So first, we have some steps. First, compute preliminary calculations. Yeah, and we'll just jump right into this table here. So first, we need deviation scores. So we need to calculate m of x and m of y, the means for both variables. And if we do that, we find that the mean of x is 4, the mean of y is 532. Now we're going to do deviation scores, just like we've done sum of squares in the past, right? So 6 minus, what was our mean? 4 is 2. 4 minus 4 is 0, so on and so forth. Same thing for y. Now sums of squares. So first we're going to multiply these two. So 2 times minus 52 is minus 104. 0 times minus 42 is 0, so on and so forth. Then we're going to square these values. Oh yeah, I'm sorry. This is the sum of the products of deviations for x and y. There you go. So now we'll do this. Square 2 is 4, square 0 is 0, so on and so forth. Same thing for sum of the squares y. And then we'll just plug our values in. We do that, we'll get a value of minus 0.744. Right, so you can see a pretty strong negative relationship between the two, which we predicted just by looking at the graph earlier. Effect size and correlation is wonderfully easy for the most part, and that's here it's r squared, so it's literally just the square value of r. Mathematically, the equivalent to eta squared. And yeah, just like other measures of effect size, we're stating the proportion of variance of one factor that can be explained by known values of a second factor. So in the previous example, if we square our r value, sorry, my Kansas doesn't let me say this well. We square the r value and we get this. So you can see the effect size here is smaller than the actual correlation coefficient. All right, here we could say that we conclude that about 55% of the variability in calories consumed can be explained by participants' ratings of their mood. Right, so in other words, your mood plays a big role in how much we eat. Okay, and we can test these for significance. Yeah, let's see here. Hypotheses are similar, saying there is no relationship and there is a relationship. Null is none. Alternative is there is a relationship. Set our criteria. We're going to do 0.05. I forget if I asked you to do this in the actual assignment, so I'm really tempted to skip this. So let's do it slightly faster. So degrees of freedom for correlation are n minus 2. So in this example, our n was 8, so it would be 6. Critical values we'll look up in one of our tables as per usual. Based off our degrees of freedom, we find a critical value, and then we just make a decision, right? Just like we've done with other tests. We compare our obtained value to the critical value, and here we can reject the null because our correlation, our R, is minus 0.74, and our critical value is plus or minus 0.71. Therefore, we know it's outside of that critical region, and we can reject the null. Okay, so that was that. Spearman, now we're doing categorical. Yeah, this formula looks scary, but we'll still get a value between minus 1 and positive 1. So here's Spearman's row. In this case, we're looking at ordinal variables, so there's some ranking system, or there's some order to the categories. Here, D is a difference. D is the difference between the ranks of factor X and factor Y, and N is the number of pairs of ranks. So let's do an example. So let's say that an animal psychologist, or an animal behavior psychologist, is measuring motivation in mice, and he had the mice complete 2 tasks, and these mice were deprived of food and water. Those poor mice. So one was reinforced with the food task, one was reinforced with water. So trying to see which of these is more motivating when the mice are deprived. Then they rank the mice based on their times. Fastest time is ranked 1, second fastest is 2, so on and so forth. And they assume that they'll be the same, right? That food and water will be equal motivators. And so we see our chart here. We can see these graphed out, and we see the rankings. So one mouse was first in both. Second mouse was tied for first in the food task and got third in the water task, so on and so forth. All right, so the tie is within that column. So first we need to average tied ranks. Assume the ranks are in order. Yeah. So yeah, average tied ranks. Yeah, we can go through all this. Okay, sorry, I'm rambling. The problem made no sense. So basically, one was first, one was second. I think that's what this means here. So we'll add those up, divided by the number of tied ranks is 2. So basically the average of these two is going to be 1.5. And so we'll assign that to both mice that finish first. Just mathematically, it's helping us to sort of evenly distribute our rankings. So yeah, there's all those steps. So now you can see we just have 1.5 for each of those two. It's not always going to work out this way as like a perfect 0.5. So just keep that in mind and come back to it if you'd like, if you run into this in the homework or anything. So first, difference scores between x and y. That's easy enough. 0.5, that's minus 1.5, so on and so forth. We're going to square those values. We're going to sum the squares. And then we're going to plug stuff in. And we do that, we get a positive 0.77 correlation. Same thing, we can test for significance. And here, based on our critical values, we will reject the null. Right, so pretty straightforward. And you can see at this point that we're just plugging numbers into formulas as we've always done. So hopefully this is going to be easy for you. Yeah, in this case, we have dichotomous and a continuous. So point-biserial correlation. Formula. Let's see. This is the standard deviation of y-scores. P and Q are the proportions of scores for each level of the dichotomous variable, and is a number of pairs of scores measured. So let's go into an example here. So in a study investigating how gender is related to perceptions of humor, people looked at a video of a female comedian performing a 1-minute comedy skit, and then the time they spent laughing was recorded. And the gender of the participant is a dichotomous factor, and the time spent laughing is a continuous factor, right? So one binary variable and one is continuous. Okay, and so we do that. We can see here we have 1, 2, 3, 4, 5 males, and 1, 2, 3, 4, 5, 6, 7 females, and their laughter. Okay, and so first we need to code the dichotomous factor. In this case, it was gender, with a binary assumption. And, oh, what just happened? So let's say men are coded as 1 and women are coded as 2. In that case, we had 5 men, and there were 12 total. So the proportion of men is 5 divided by 12 for 0.42. In other words, 42% of participants were men. 0.58 for women. And we'll need P and Q later. So now let's fill out our table, compute the means for both categories. Right, so just calculate the M of y and the M of x. And importantly here, we have the overall mean and then also the mean for each category, right? So my1 is the mean y-scores for men who are coded as 1. And my2 then is the mean y-scores for women coded as 2, right? So in other words, the mean of the top 5 and the mean of the bottom 7. Calculate deviation scores. Yeah, so you can go ahead and do that for all these. Sums of squares, sum them, right? Again, same general principle, just a slightly different setup. We'll plug stuff in. Here we'll get a negative correlation, but in this case, it's meaningless because gender is dichotomous, so we can just ignore that. And then, yeah, test for significance, basic stuff, right? In this case, it was not significant, right? Last one is 2 dichotomous or binary variables. Let me see what I need to note here. So yeah, so in this case, we're looking at a matrix like this. So A, B, C, D, big A, big B, big C, and big D, right? And then we're just going to plug it all in here. And so yeah, so basically you'll take the values from this table and plug them in. I'll let you come back through this if you'd like to look at the example specifically. Yeah, and actually, yeah, I'll just end there. Because it is really straightforward. Just follow the slides, follow the instructions, and you'll get there. If you have any troubles, just let us know. Generally speaking, when we report correlations, we do this using a correlation table. It's something that is kind of standard practice in any sort of study, is to include a correlation table with the results of all of your variables that make sense to include in a correlation table. And so you can see this is an example from my dissertation, just to give you an example of what this looks like. So here I have all these variables. This was longitudinal, so I have time 1, time 2, time 3, so on. Mean, standard deviations, and then the correlation matrix. And you can see we generally use asterisks to indicate which ones are significant at the 0.01 and 0.05 level. And there you have it. I'm sorry if I moved too fast there, but I didn't want to drag on forever telling you what you can read yourself. So like I said, follow the instructions, proceed with caution, and then just let us know if you have any questions. Thanks. We'll see you around.